So here I think this is the internal convection. I think if we mute our video unless we're currently speaking ASL, then I think the interpreters will be larger. So I'll give you a second to mute your video. Okay, so the first question in the quiz, water at 20 degrees Celsius flows through a 1 centimeter by 2 centimeter channel, so it's some kind of rectangular duct, and we're given a flow rate in volumetric flow rate. Assume water is in contact with all surfaces. Which of the following is the corresponding Reynolds number? And we're given a bunch of properties. So we know that our Reynolds number is given by these equations here. And we know that we can use the hydraulic diameter because it's a cross-section that's a rectangle. So we can put some data in there. And once we have the hydraulic diameter, we can calculate the Reynolds number. And I get a Reynolds number of 64.4, which is one of the answers. For internal flow, which of the following is the critical Reynolds number, where laminar flow transitions to turbulent? So the key part here is, I guess, we're talking about internal flow and not external flow. So for internal flow, we have a transition of 2,300, whereas for external flow, we have a transition at about 500,000. So the next problem, water at 20 degrees Celsius flows through a 2 centimeter diameter, 10 meter long tube at a particular flow rate. Which of the following best describes the flow conditions? So all of these answers, so we got to figure out if it's turbulent, laminar. We have to figure out if the velocity profile is developing or developed, and then if the thermal profile or the temperature profile is also developing or developed. So the first thing that we want to do is find our Reynolds number. So we're given enough information to calculate the Reynolds number. We see that the Reynolds number is less than 2,300. So we know that this is laminar flow. For laminar flow, we have different developing lengths or entrance lengths for the hydrodynamic and the thermal boundary layers. So here I can calculate my hydrodynamic entry length as 1.27 meters. So the pipe is 10 meters long, so most of the pipe is fully developed hydrodynamically. Then we can do the same thing for the thermal boundary layer. We can take the length that we have for the hydrodynamic boundary layers and multiply by our Prandtl number, which in this case is 7, and we get that it takes about 9 meters for the flow to develop thermally. So most of the flow is developing, most of our 10 meter long pipe is developing, and a little bit at the end is developed. So in this case, we have a laminar flow that's hydraulically fully developed and thermally developing for most of the pipe. For steady state internal flow of an incompressible fluid, in which region along the tube is convection coefficient constant? So we know that the convection coefficient becomes constant once we're thermally developed. The convection coefficient is decreasing up until we have a fully developed flow, and then once the flow is fully developed thermally, we get a constant convection coefficient. So the answer here is A. Water flows at 5 kilograms per minute through a thin-walled 3 centimeter diameter, 2 meter long tube whose inner surface is held at constant temperature. The mean inlet and outlet temperatures are given, and we know that a certain amount of heat is being transferred from the pipe to the water, and we're asked what the average convection coefficient inside the pipe is. So here we see that we have a boundary condition that's constant temperature. So if we're trying to find if we have a pipe that's constant temperature, then we can use this equation that involves the log mean temperature difference. So this looks just like Newton's law of cooling, where it's HA times some kind of delta T. But because we're going along this pipe and the pipe has a constant temperature, but the fluid temperature is changing, the delta T that we use is the log mean temperature difference. So here we can isolate for the convection coefficient. We know enough information to calculate the log mean temperature difference given by this equation here. So we can find that the log mean temperature difference at the length that we're interested in. And then we put that into our equation and we find a value for H, and that value is on our list. So we pick D. So that's the end of the quiz. Does anybody have any questions about the quiz? All right, we'll start moving towards new material here.
I have a question,
sure,
Marcus.
go ahead.
I'm just going to go ahead and type it in the chat.
Okay. Here, I'll see if I can bring the quiz back up. So in the chat, I don't see anything yet, but that's okay. Okay, so for the entrance length, hydrodynamic and thermodynamic, when calculated the value of each of this, how would I know if this is fully developed or developing based on the number? Okay, so that number, let's see if I can bring up the lecture. So that number is the length down the pipe at which the flow becomes developed hydrodynamically or thermally, depending on which of these equations you're using. Let me bring up the slides for internal convection. This looks like external.
Okay, so it can be either hydrodynamic or thermal.
Yeah, so the entrance lengths are different for the flow, for the velocity profile, and for the temperature profile. So this first value here, this tells me that after 1.27 meters, we have a fully developed velocity profile. So after 1.27 meters, we would get that sort of parabolic velocity profile that we're used to from laminar flow in a pipe. But for the first 1.27 meters, there'd be this core of the flow that would have the velocity that was coming into the pipe. And then similarly, for the thermodynamic, or for the thermal entrance length, we get that sort of core of the flow where the temperature would be constant at whatever T infinity was, or T in, I guess, was, of the fluid coming into our pipe. And the core of the flow is going to maintain that temperature until we get to almost 9 meters into the pipe in this case. And then we would have the temperature profile that we would expect from a fully developed thermal flow. Does that make sense?
Yep, gotcha.
Just want to make sure the chat's open. Okay, so with that, we'll go on to the new stuff. So, I like to share what happened in our weekend, as we move through. So the first thing, like I said, I've been sort of trying to take up baking. I think there's something satisfying about learning new skills and about, creating something. So I made English muffins, which I'd never done before. They turned out pretty good. So these are, we had our Sunday morning breakfast. We had Egg McMuffin sandwiches. So this is one that I made with a fried egg in the middle. So it's pretty delicious. We made those French fries again. So these are pretty fun if you've got an oven and some potatoes. So they work pretty good. But I think the big news for us on the weekend, my daughter Emily, so my 8-year-old, was riding her bike, and I guess with my older daughter and then one of the friends in the neighborhood, and she kind of swerved to avoid somebody and ran right into a mailbox. So she cut herself open pretty good. So she ended up with sort of 7 stitches kind of around the, sort of in between her eyelid and her eyebrow and kind of around her eye. So, it ended up being everything okay, but it was a pretty stressful Saturday. We called some friends of ours who, work in healthcare, and they suggested a particular hospital to go to because they've got, less cases or something. But, when my wife took her there and I stayed home with the other kids, she said that it was nice because there was almost nobody there. So that's nice, just people that work there. But it's just a reminder, I guess, to be safe out there. So, but Emily's doing well. She's okay. She's in good spirits. But it was kind of an eventful weekend. So our Sunday was pretty laid back. We just stayed in on Sunday, right? Like everybody else. So the new material that we're going to talk about today is we're going to learn about heat exchangers. So you might remember that we talked about heat exchangers kind of a lot in thermodynamics. So whenever you took it, I don't know, maybe you've repressed these memories, but we did talk about heat exchangers in thermodynamics. And when we were in thermo, we were saying that the reason why we care about, thermodynamics and heat exchangers is that they can be like Lego blocks in this big cycle, right? So we can use these Lego blocks to make really cool things, right? Like power generation cycles, right? So we can, if we understand things like heat exchangers, they're one component that goes into making things like power plants, right? And one of the components that we talked about in thermodynamics were heat exchangers. And you might have seen a picture that looks like this one down in the bottom where we have a shell. So we have maybe there's some hot fluid that's moving around this tube that's carrying cold fluid, or maybe vice versa. And these, it's a bit like Ghostbusters where the fluid streams don't cross, right? They don't mix in this case that's shown here, but there's still heat that's transferring, through this thin-walled tube in, between these two fluids. So in thermodynamics, we talked about two different kinds of heat exchangers. So the first one is kind of this direct contact mixing where we, maybe we have a hot fluid coming in the top and a colder fluid coming in on the side, and they come together in the mixture and they're actually mixing. So if you have maybe water and it's both water and they mix together, then, you'll have hot and cold coming in and warm going out. I kind of think about this as my grandfather used to shave in a sink, right? And the sink had a hot tap and a cold tap, and he'd mix the hot and cold water together in the basin, right? So that's this kind of direct contact heat exchanger. But we're not going to talk about those in this class. We're more interested in shell and tube or counterflow heat exchangers in this class, which is, sort of like this picture here on the right, where we have flow that's separated. So we have some hot channels and some cold channels, but they don't mix. And oftentimes you'll have different fluids. So if you think about maybe the radiator in the front of a car, you have your radiator fluid that's moving through one side of the heat exchanger, and then your car, as it's moving, the air flows over sort of the fin apparatus that you see in a radiator, and then there's this kind of what do we call a cross-flow heat exchange between these things. So we're more interested in something that looks maybe like a shell and tube heat exchanger, or we'll talk about different geometries as well, but where our flows don't physically mix, but they still transfer heat between the different flows. So in thermodynamics, we would have said, okay, let's use the first law and try to figure out what's going on with the heat exchanger. So we would have said, that it's at steady state. There's no work being done. So there's no fan blades. There's no power produced, and you don't have to plug it into the wall for it to work. We say that the whole heat exchanger is adiabatic. And this can be a little bit confusing because we're definitely transferring heat. Remember, adiabatic means like perfectly insulated. So what this means is that all of the heat that goes from the hot side of my heat exchanger goes into the cold side of my heat exchanger, and that none of that heat is lost to the atmosphere. So we're still transferring heat, but we're assuming that all of it is captured. Our control volume encompasses the entire heat exchanger, so all the heat lost from the hot side goes into the cold side. Like most problems in thermodynamics, we would have neglected changes in kinetic and potential energy, assuming that these were small compared to the changes in the enthalpy. So when we do that, we see from thermo that we get that the sum of m dot times the enthalpy in minus the sum of m dot out times the enthalpy out is equal to 0. This is just saying all the energy that comes in goes out. Or we could look at it this way, and we can arrange our mass flow rate terms by which fluid they are. And if we do that, we get this equation on the bottom, where here we'd have a separate mass flow rate for the air that's moving through our heat exchanger, and another mass flow rate for the refrigerant that's moving through the tube in our heat exchanger. And then we can say all of the heat that comes out of our air goes into our refrigerant, or vice versa. So that's why we have this negative sign here. It's basically saying that the magnitude of heat that we lose from the hot side is equal to the magnitude of heat that we gain on the cold side. So if I'm talking about heat transfer, right, we do usually assume that there's no phase change and no losses, right? So we assume that it's adiabatic. So we're going to, if I make both of these terms positive, if my delta T's are always T hot on one side minus T cold on the other side, then I don't have to worry too much about my signs. I'll just try to make all of these heat transfer terms positive. So that's what we did in thermodynamics, but now we're in heat, right? So we know a little bit more. We're a little bit more experienced, right? Maybe we've leveled up a little bit. So when we looked at heat transfer, or when we looked at thermo was great for trying to analyze cycles. So we knew what was coming in and we knew what was coming out of our heat exchanger. And if we knew those two things, we could tell you how the heat exchanger worked, right? We could use it as one of these Lego blocks in our big sort of master builder kind of cycle that we were working on, right? And this is great because it let us analyze different systems. But you know, and if you work for a power plant, that's great because you're just going to go into some catalog or talk to some distributor and buy a heat exchanger. But if you work for the company that's designing the heat exchanger, you need to really understand how it works, right? Because if you understand how it works, you know, maybe you're talking to a customer and they say, I want this temperature at the inlet and this temperature at the outlet, but you have to figure out how big the heat exchanger needs to be, right? How much heat is it going to transfer? Right? So we're going to teach you in heat in this class how we design heat exchangers. Right? And when we do this, we remember that we're transferring flow between basically two internal flows. So we need some kind of effective heat transfer coefficient multiplied by some area multiplied by the temperature difference between our hot and cold fluids, because that's where we're transferring heat from. So a lot of times when we're talking about heat exchangers, we're going to try to figure out the size of the heat exchanger. So how much heat transfer area do we need? And to do that, we'll need to know something about an effective heat transfer coefficient, and then hopefully we can find the size of our heat exchanger. So in heat transfer, we need to do more than we did in thermo. We're not just analyzing things. We're trying to learn enough so that we can design heat exchangers to get the kind of performance that we want. So there's some things that are important for us to think about. So we want to know about the plumbing. So what kind of heat exchanger are we talking about? So that's going to be important. We want to know the size because like we've said sort of throughout the whole course, the amount of area that we're transferring heat through really matters for how much heat we transfer. And then we're going to talk about something called effectiveness. So effectiveness, this is a little bit like fin effectiveness, where we're going to talk about how much heat is actually transferred versus how much heat is transferred, or how much heat could be transferred. So a maximum heat transfer. So first we'll look at plumbing. So the plumbing, we can think about, even if we have two heat exchangers that look the same, right? So these are both shell and tube heat exchangers, but how you set up the inlets and outlets matters, right? So we can do this in parallel flow, where if you can see in this image, the flow in the shell on the outside and the flow in the tube are going in the same direction. So if the shell is the hot, then the hot fluid on the shell at the inlet touches the cold fluid inlet of the shell. But we could take this same device and we could set it up a little bit differently so that the hot fluid in my shell is touching the exit of the cold fluid in my tube. And the hot fluid in the exit of my shell is touching the inlet of the cold fluid in my tube. So these two ways that we can set it up, either in parallel flow, or sometimes called co-flow, or in counterflow. There's also other kinds of heat exchangers that we can design. So this is a cross-flow heat exchanger. So here in the tubes, we can see that there's flow coming through these sort of copper-colored tubes. And then we have these grids, right, these fins, and there's air that's going over our tube bundle here. So because these flows are at 90 degrees to each other, we call them cross-flow heat exchangers. We can also have more complicated shell and tube type heat exchangers. So here there's a tube bundle, right? So we have this one tube or this one flow in the tubes. It's coming in the inlets and then through all of this big tube bundle. And then it goes out the outlet. And then we have flow that's coming in the shell and it's going all over this this tube bundle. Now, one of the things that's done here is we have things called baffles. So you can see these baffles are like the walls that are in there, and that forces the flow on the shell side to sort of first move down and then up and then down and then up. So it has to pass over the tube bundles multiple times. So in some of these correlations, we'll see something called shell passes, and those shell passes only come when we have baffles. So that forces the flow in the shell over the tube bundle multiple times. Another thing we'll have to worry about is sizing. So obviously how much heat transfer area we have changes how much heat we're going to transfer. We know for convection that we have some kind of H times the area times delta T. So if we know the heat transfer, we could find the area. Or if we knew the area, then we could find the heat transfer. So these two things are related. So if you're looking for a particular heat transfer and you're designing a heat exchanger, you're going to have to try to figure out what kind of area you're going to need to sort of achieve that goal, right? And this is going to be different depending on the type of heat exchanger that you would have picked. So this is interesting because this would have been our third case study. So we're not going to do the third case study, but the third case study would have been for you and your team to design a heat exchanger given some requirements, right? So you would have had to pick a particular type of heat exchanger, try to do some analysis, and figure out how much area you would need to make your heat exchanger. And you would have had to sort of fit that heat exchanger in a particular volume. So it's like, you already had a case to put it in, so you had to make it efficient enough so that your area was small enough that it would fit. So different heat exchanger types have kind of like different, I hesitate to use the word efficiency because it has a particular meaning, but you can get a particular amount of heat transfer for a given area depending on which heat exchanger type you pick. Another thing that's pretty important for these heat exchangers is the concept of effectiveness. So our effectiveness is going to be our actual heat transfer that we get from our heat exchanger divided by our maximum heat transfer that we could at least theoretically get from the heat exchanger. So it's a little tricky to always figure out, like, okay, what's going to be our maximum heat exchanger, right? So this is, if we have this is a graph for a parallel flow shell and tube heat exchanger. So you see that because at the beginning we have the hottest temperature and the coldest temperature touching each other, but over time these temperatures get closer and closer together, right? So if we could get the maximum amount of heat transfer, that would be at a case where what we're going to call the specific heat rate, so the mass flow rate of one side times its specific heat, is much, much bigger on one side than the other side. So if that specific heat rate was much bigger on the cold side, then the cold side temperature basically wouldn't change. The flow is either moving fast enough or that its specific heat is so high it can absorb so much energy before the temperature goes up that its temperature doesn't change. It's almost like a reservoir. Then what would happen in the ideal case, right? Then our hot temperature, which we can see in this dashed line, it would go from all the way on the hot side, would go all the way from the hot temperature. And if we transferred the most possible heat we could, then that hot side temperature would end up equaling the cold side temperature at the outlet. So that's the biggest amount of heat that we could get, is if one side of our heat exchanger changes its temperature so much that it goes all the way to the inlet of the other side. So that's our maximum heat exchange. So when you think about this, if you think about parallel flow and counterflows, what we'd like to do is get to a point where, in this case, how could we make the hot outlet approach the cold inlet? So this is why plumbing matters, or one of the reasons why plumbing matters. So if we look at the counterflow, what happens is if our hot side is, let's say the hot flow is in the middle, right? So the hot flow is going through this tube and the cold side is going through the shell. So then what happens is the hottest temperature coming in sees the hottest temperature of the cold side, right? So we're going to keep transferring heat as we move down the pipe. And at the end of the pipe, we're going to get the coldest part of the hot side is touching the coldest part of the cold side. So if you made this tube long enough and your cold side temperature didn't change, then you'd have a better chance of getting your hot side outlet down to your cold side inlet. So here you can see that we get a bigger temperature change on the hot side when we run in counterflow than we do in co-flow or parallel flow. So the reason is because at the end of the tube, we're cooling the hot side down more than we would if it was in parallel flow. So here this DQ term, so the amount of heat that we're transferring at a particular length down our tube, stays more constant. Whereas in a parallel flow, we get a large DQ term at the beginning because we have this really big temperature difference right when we enter. The hottest part of the hot flow and the coldest part of the cold flow are touching each other. But then as we move down the tube, this DQ term diminishes much more rapidly. So typically, we like counterflow heat exchangers better than parallel flow heat exchangers. But how do we find Q or DQ, right? So if we were thinking about this in terms of thermal resistances or in terms of internal flows, we could look at flow that looks something like this, right? So here we have a hot flow coming through this thin-walled tube, and then we have another tube on the outside that has a cold flow in it. So this is kind of this annular flow around the outside. So in this case, the fluids aren't directly mixing. So if we were trying to do this problem in Module 1, we would have said, okay, let's draw out a resistance diagram, right? And in this case, there's at least 3 resistances in the problem. There's a resistance from convection for, in this case, our hot fluid to go to the thin wall, right? So that's this resistance, the resistance on the inside. There's resistance as we pass through the wall. So this is resistance from conduction as we pass through this thin wall. And then there's resistance from convection as we go from the outside of this thin wall to the cold fluid. So there's 3 different resistances, right? 2 of them are convections and 1 of them is conduction. And if we drew a circuit, it would look like it does in this picture down here. So we can find the total resistance, right? So our total heat transfer is going to be proportional to the total resistance. So, we can find the total resistance by adding these 3 up because they're in series. So if we add them up, it looks like this, right? And this is a little bit tricky because all of these area terms are different in this case. If it's a cylinder like this, all of these area terms would be different because the area on the inside of the tube is slightly smaller than the area on the outside of the tube. And then the area for the conduction is actually the surface area of the tube, right? So these are all different area terms. So one of the things that we do to make our lives easier is we're going to say that the wall is so thin that it doesn't give any thermal resistance. So if we look here in the conduction term, we have the thickness of the wall is on the top, right? It's in the numerator. So if it's so thin that it goes to 0, then that conduction term drops right out. And the area on the inside of the tube is basically the same as the area on the outside of the tube if you had this sort of paper-thin wall of the tube. So then our problem becomes a little bit easier where we approximate the total resistance by calculating the heat transfer coefficient on the inside of the tube and the heat transfer coefficient on the outside of the tube We say these areas are then the same. And now that we know how to do internal flow problems, we could see a problem where maybe we're given H in, or HI, or H out, HO, and we could also see a situation where maybe we could calculate these things based on what we know about internal convection. So here, if we know our total resistance, then we can also, instead of thinking about these as two different heat transfer coefficients, we can find an effective heat transfer coefficient, just like we did earlier in the class when we were talking about U. I think we did that when we were talking about thermal conduction problems. So here, this U is an effective heat transfer coefficient, and we can define that as 1 over R double prime. Or if we add up the, well, follow this equation, right? Because there's two different reciprocals in there. But if we do that, then we'll get an effective heat transfer coefficient, or U. Right? So this is great if we're given H in and H out. But we could have situations where maybe we're only given one of these. Maybe we're not given either of them, and you would have to calculate them. So if you have to calculate them, then you would use this same convection flow chart that we've been using for the last 2 weeks. We'd have to figure out if it's internal flow, so flow inside of a tube. External flow could be maybe flow over a tube, right? We talked about some external flow over cylinders. So you could find internal or external heat transfer coefficients here. So now, how would we find the heat? So if we assume that we're at steady state, adiabatic, that the fluid properties like specific heat are constant, that the heat transfer coefficient is not a function of x, right? So that would mean that we're assuming that the flow on both sides of our heat exchanger is fully developed for most of the time. So neither of those heat transfer coefficients would be changing with position. And if there's no axial conduction, so that there's no conduction down the length of our tubes, then we would get the same equation that we got in thermodynamics, where we would get m dot times Cp delta T is equal on the hot side and the cold side, provided that I'm taking the magnitudes of those terms. So in heat transfer, we're sometimes going to simplify this a little bit so that m dot times Cp becomes big C. And that big C is called the fluid heat capacity rate. So it's kind of like the larger this is, the less temperature difference we would expect to see. So let's say that the right-hand side of this equation stays constant. Then what we could do is we could change CH. So if we made the mass flow rate bigger, or we increased the specific heat, then we would get a smaller temperature difference. And if m dot or Cp was smaller, then we would expect a larger temperature difference. So that's this fluid heat capacity rate. It's kind of telling us how much temperature difference we're going to need to achieve a given heat flux or heat transfer. So that's how we would find in like a parallel flow or a counterflow heat exchanger. That's how we would start to find how much heat we need, right? But we also might want to find out how much area we need, right? So here we'd have to look at this and we'd say that, the amount of heat that we're transferring changes as we move down our pipe. So this actually becomes a differential equation because the local temperature difference between the hot side and the cold side is a function of position down the pipe. So we're going to define Q as the effective heat transfer coefficient times the surface area, so the area of heat transfer between these two fluids, multiplied by the log mean temperature difference. So the log mean temperature difference is going to be delta T1 minus delta T2 divided by the natural log of delta T1 divided by delta T2. Now, if we're talking about a parallel flow heat exchanger, so the tricky thing here, I present it this way because then this will work for parallel flow and counterflow heat exchangers, that the form of the equation is the same, but the way we define delta T1 and delta T2 is a little bit different depending on what the geometry of our heat exchanger is. So here, if it's parallel flow, delta T1 is the hot inlet minus the cold inlet, And delta T2 is the hot outlet minus the cold outlet. See, they're both on the same sides, right? So the purple stuff is all on the left-hand side here, and the blue stuff is all on the right-hand side. So our delta T1 is always going to be pinned to the hot inlet. And it's also, the delta T's are going to be the T's that touch each other at the inlet of the hot side and the T's that touch each other on the outlet of the hot side. So if I have counterflow, I end up with the same equation, except that my delta T's are different. So now my delta T1 still touches the hot inlet, but now the hot inlet is communicating with the cold outlet. So now delta T1 is T hot in minus T cold out. And the hot outlet now is communicating with the cold inlet. So my delta T2 is going to be T hot out minus T cold in. And one of the examples that we'll do in class is we'll look at the difference between a counterflow and a parallel flow heat exchanger given the same inlet temperatures. So you can use log mean temperature differences for other geometries as well, although I'm going to recommend that you don't. But if you do, it's possible. So there's different kinds of geometries you can have. So this first one, this is a shell and tube heat exchanger where the shell makes more than, or the tube makes more than one pass. So the tube goes to the end of the shell and then comes back, right? And this is even more, right? So you could look and you can find a geometry that looks like what you're doing, and you can use this log mean temperature difference method. It's just you'll have this factor F. So you sort of have to multiply by F, right? So now this isn't the log mean temperature difference equation we had before, which was just UA delta T log mean. But here, if you're using one of these funny geometries, then you use UA times F delta T log mean. So we do this sometimes in experimental work. We say like, well, I kind of know the form of what the equation should look like, but then I'm just going to multiply by some kind of fudge factor, right, or a correction factor to get an answer that looks close to right. So here, depending on your equation, you could read this graphically depending on your geometry. But we're gonna talk about a different method called the effectiveness-NTU method, which I think is better for these more exotic geometries. So when we're doing heat exchanger problems, one of the things that we'll have to do is determine what's the right tool, what's the right solution method, right? So we use the log mean temperature difference method in certain cases. So we can use log mean temperature difference if we know the inlet and outlet temperatures, and then I can use it to find UA, right, or to find Q. Depending on, usually I'll either know the size or I'll know the heat transfer, and I'm trying to find the other thing. But I would suggest that you only use the log mean temperature difference method when you're trying to solve parallel and counterflow heat exchangers. If you have a more exotic heat exchanger type, I'm going to suggest that we use a different type of analysis method, which I'll talk about next. So if I don't know the inlet and outlet temperatures, or I'm using sort of something that's not a simple parallel or counterflow heat exchanger, then I'm going to suggest that we use the effectiveness-NTU method. So this involves knowing the effectiveness, right? So we've defined the effectiveness as the actual heat transfer divided by the maximum heat transfer. So we can think about the heat transfer as being equal on both sides, right? Because we're assuming that our whole heat exchanger is adiabatic, that we're not losing any heat to the outside environment. So that means that all the heat that I transfer from my hot side goes into my cold side, right? Or I can calculate Q either of these two ways, remembering that capital C is equal to m dot times Cp. Now my maximum heat transfer is going to be, the most heat transfer I get is if I take the side of my heat exchanger where the temperature changes more easily, right? So that's going to be the side of my heat exchanger where big C is smaller. So I got to find big C min, and then the most heat I could get would be if the side of the heat exchanger where the temperature is going to change more changes as much as it possibly can. And the most the temperature could possibly change is going to be the hottest temperature in my heat exchanger minus the coldest temperature in my heat exchanger. The hottest temperature is the hot inlet, and the coldest temperature is the cold inlet. So Q max is going to be big C times T hot in minus T cold in. So to do this, I have to calculate big C on both the hot side and the cold side and figure out which side is big C min. So the other thing that we're going to use, this is called the effectiveness-NTU method. So we need to know about effectiveness, but we also need to know about NTU, which is the number of transfer units. It's something about how much heat gets transferred in our heat exchanger. So NTU is the heat exchange rate, or heat exchanger heat exchange rate, divided by the minimum fluid heat rate. Right? So this is going to be the actual amount of heat that gets transferred is UA times delta T. Right? And on the side of C min is going to be C min times delta T. Right? So the delta T's kind of drop out here. So we get U times A divided by C min. And that's going to be our number of transfer units. It gives us some idea of how much heat is being transferred. Right? So this is, some kind of calculation, but why do we care? Right? The nice thing about NTU is if we knew NTU, right, we see that it's a function of the area. So if I'm trying to find the area of my heat exchanger or the size of my heat exchanger, this could be a useful thing. Right? And it turns out that there's a relationship between effectiveness and NTU. That effectiveness is a function of the number of transfer units and CR. So CR is the ratio C min divided by C max. So CR should always be less than 1. If you're calculating CR and you get a value bigger than 1, it means that you did it wrong. So you need to take the inverse of that. So for this is the textbook shows for parallel flow and for counterflow heat exchangers, there's a graph, right? So effectiveness is a function of NTU depending on what your CR is. So this is kind of graphically showing that information. And the textbook does this kind of graphical thing for different kinds of geometries, right? So we can use effectiveness NTU to try to find for any kind of heat transfer geometry. So this is nice, although it's a little faster to do the log mean temperature difference if I can, right? But I don't like to do that for complicated geometries. So the process, if we're trying to find how much heat our heat exchanger is going to transfer, right? Then we want to pick the geometry. We want to find all of our big C's, so big C min, big C max, and then the ratio of the two. We'll calculate NTU by the definition, right? So that's going to be UA over C min. We'll find effectiveness using this relationship, using a chart like this or maybe a correlation between effectiveness and NTU. And then when I know effectiveness, if I can find Q max, because remember effectiveness is Q actual divided by Q max. So if I know my effectiveness and I know my Q max, then I can find Q actual. So this is a flow chart. We're going to have two different flow charts for the effectiveness NTU process, and it's going to depend on what goal we have. So if we're trying to find the amount of heat that we transfer, then we're going to use this flow chart. Now, the cool thing about effectiveness NTU is that it works really well, not just for parallel and counterflow heat exchangers, but for any kind of geometry where we have some kind of relationship between effectiveness and NTU. So the textbook gives you a bunch of figures where you could try to read this graphically, but I'm going to suggest that you don't try to read this graphically because the textbook also gives you a bunch of different correlations. So there's two different tables. I think it's 11.3 and maybe 11.4. I think I'll show the other one later. But this table, 11.3, is given effectiveness as a function of NTU and CR. So if I was trying to find the amount of heat that my heat exchanger transfers, then I'm going to find NTU by the definition and use NTU and CR to find effectiveness. So I need to pick the type of heat exchanger that I have, whether it's parallel flow or counterflow, whether it's shell and tube, or whether it's crossflow. So then I can just go and pick the right equation, and then I have that correlation, and then I can find effectiveness. So that's how I'm going to use the effectiveness NTU process to find the amount of heat that we transfer. But I might also want to use it to find how big my heat exchanger should be, right? Or how much area my heat exchanger should have. So here we have a different flow chart, although it's still similar. So first we're going to pick the geometry, because that's going to tell me basically which correlation I'm going to use to, to find the relationship between effectiveness and NTU. Again, the first two steps look the same, so I'm going to find all my big C's. But now I'm going to find effectiveness from the definition, because usually if I'm trying to find how big, the question would be, how big does my heat exchanger have to be to transfer this amount of heat? So I would know Q actual. So if I know Q actual and I can find C min, then I can find Q maximum. So I can find effectiveness from the definition of effectiveness. And then I'm going to use the relationship between effectiveness and NTU to calculate the NTUs. Now, in order to do this, when I find NTU, remember in NTU, there's that effective heat transfer coefficient in it. In some problems, we're going to be given the effective heat transfer coefficient, or maybe given H on one side and the other side of the heat exchanger. But I might have to use my understanding of how to find convection coefficients to find U as well. And then once I know what NTU is, I can use the definition of NTU to find A. So in this case, I'm going to want to, if I'm trying to find the size of my heat exchanger using effectiveness-NTU method, then what I'm going to want to do is look at table 11.4 over here. And this is almost the same. These are all the same equations. They're just rearranged a little differently so that NTU is on the left side instead of effectiveness being on the left side. So again, if I know my geometry and I can pick the right equation for my situation, then I can sort of plug the values in here and get NTU. And then once I know NTU, I can use the definition of NTU to find the area. So that's the end of the new material in the lecture. I'll pause for a second here to see if anybody has any questions, and then hopefully we can get one example done, because I think it'll make a little bit more sense once we start to do examples. Okay, I'll close this file. So this is the first example. It's sort of like last week where it's the second one on the handout, because the first one on the handout is a little bit long, and I wasn't sure how much time we'd have to do this problem. So here we have a cross-flow heat exchanger. So it says exhaust gas from a furnace is used to preheat the combustion air supplied to the furnace. Right? So this is nice. So you're taking the hot air that's leaving this furnace, and you're using the heat that's still stored in there to preheat the air that goes into the furnace, so you burn less fuel, right? And that's good for those of us who like to live on Earth. It saves us a little bit of money, but also reduces emissions. So the exhaust gas, we're given the flow rate and the inlet temperature, and it passes over this bundle of tubes, right? So the exhaust gas is kind of this green arrow, and the inlet gas is going through the tubes. So this is a cross-flow heat exchanger. And we're given sort of how much, we're given some information about the flow rates. So the tubes are unfinned. So we could have, this is sort of drawn in a grid, right? You could have, like in your radiator, there's fins, right? So then all the flow on this green flow would be separated into different chambers, basically, almost different channels. But that's not the case here. So the tubes are unfinned, and the overall heat transfer coefficient is 100 watts per meter squared Kelvin. So overall your heat transfer coefficient is capital U. So that's nice. We won't have to do any internal convection analysis here. Determine the total tube surface area required to achieve an outlet air temperature of 850 degrees Kelvin. So the exhaust gas and the air may each be assumed to have a particular specific heat. Right? So so here we have a hot inlet temperature that we're given, right? So I sort of drew, or at least took a picture from the internet. We know that the inlet temperature on the hot side is given. The inlet temperature on the cold side is given. And the outlet temperature on the cold side we know, right? and we know U, and we know the CP values. And we're asked to find the area of the tube. So how big does my heat exchanger have to be in order to get this much heat transfer? Because they didn't spell out what the heat transfer is, but we have enough information to calculate it because we know what's going on the cold side. So assumptions we'll make in this problem, that the system is at steady state, that the fluid and material properties are constant, that there's no losses to the surroundings, that it's mixed on the cold side and unmixed on the hot side. So this terminology can be a little bit confusing. So if it's unmixed, that means I took my flow and separated it into different tubes or into different channels. So if it's unmixed, it's because the flow in one tube can't mix with the flow in the other tube. So on the hot side here, our flow is unmixed because the hot side was going through the tubes. The cold side is going over the tubes, but because there's no fins on the tubes, it hasn't been segmented into different channels. So it's mixed on the cold side because theoretically, some fluid molecule in the top right-hand corner could go down to the bottom left-hand corner. So it could move from side to side. So I'm going to suggest when you do these heat exchanger problems, you start off by thinking about a 2x2 matrix that looks like this. So on the vertical side of our matrix, we have the objective. So for these heat exchanger problems, we're either trying to find how big the heat exchanger needs to be or how much heat the heat exchanger transfers. And then on the horizontal side of my 2x2 matrix, I need to figure out what the method is. So I can use the log mean temperature difference method, or I can use the effectiveness-NTU method. Right? And you can see, so in this picture, you can see I have different sort of flow charts depending on what I'm trying to find. So in this case, the problem asks us to find how much heat transfer area do we need. Right? So we're trying to find the size of the heat exchanger. And because it's a cross-flow heat exchanger, it's possible for me to do this with the log mean temperature difference method, but I don't want to mess around sort of reading graphically off, charts that are in the textbook. So I'm going to say for anything that's not a parallel flow or counterflow heat exchanger, I'm going to try to use the effectiveness-NTU method. So now I know which process to pick, which means that I know which flow chart I'm supposed to follow. So I'm trying to find the general effectiveness-NTU process for sizing a heat exchanger. And that looks like this. I need to pick the geometry, find my capital C values, find effectiveness from the definition, use the correlation between NTU and effectiveness, and use the definition of NTU to find A. So the first thing that I want to do is pick the geometry. So this is what the problem looks like. We have a cross-flow heat exchanger. I know that the hot flow is unmixed or separated into tubes, and the cold flow is mixed or not separated into tubes or channels. So I want to find NTU as a function of effectiveness. So I look here on table 11.4. I look through and I'm trying to find cross-flow heat exchangers. So now I have two different equations that I could pick. I know that my hot flow is unmixed and my cold flow is mixed, but that's not how these equations are set up. These equations are set up based on whether C min is unmixed and C max is mixed or unmixed. So I need to know if my hot flow is C min or if my cold flow is C min, and then I can pick the right correlation here. So I need to know which of my fluids is C min and which of my fluids gets C max. That's the next thing on my list. So my flowchart's working anyway, at least for this problem, right? So this capital C is m dot times Cp. So on my hot side, I know my mass flow rate is 15 kilograms per second, and the Cp on both sides is 1,075. So I can multiply these things together, and I see that my big C, or my fluid heat capacity rate, is 16,125 watts per degree Kelvin. Now my big C on the cold side, I can do the same thing, but now my mass flow rate is only 10 kilograms per second. So I get a smaller value on my cold side. So then big C max is the bigger number here, and big C min is the smaller number. And then I know that CR, so I need to find the ratio of these two things. It's always less than 1, so it's going to be big C min divided by big C max. And in this case, it's 2/3. So this is nice. I have my values for all my big C's. The one thing, if you're watching the video that I posted for this already, I think I messed up the units here. I forgot to cancel the kilograms. So my units for big C in the video that's posted on the My Courses website is watts per kilogram Kelvin, and that's incorrect. And I think I carried that mistake through the whole problem. So just watch the units and do better than I did in this example. So now I can look back at these correlations and I see that C min is my cold side, and C max is my hot side. So here, so again, there's another mistake in here. I wrote these both as C mix or C max. So C min is mixed and C max is unmixed. And because of that, I can pick this equation for NTU. So now I can find NTU if I know CR and I know effectiveness. And the nice thing is, in my process, I've already found CR. So if I knew what effectiveness was, then I could plug this all into my calculator and find a value for NTU. So the next thing that I have to do is find effectiveness, which is the next thing on my flowchart. So I'm going to find effectiveness. That's the actual heat transfer divided by the maximum heat transfer. So here we can find the actual heat transfer because we know the temperature in on the cold side and the temperature out on the cold side. So a problem might not come straight out and tell you how much heat is being transferred, but you look for the side of the heat exchanger where you know the most information. So we've already calculated big C cold, so I'm just going to plug that in here. And I know my T cold outlet minus my T cold inlet. Again, I'm taking delta T, so it's positive. So I get a positive value for heat here. I put these numbers into my calculator, and I get the amount of heat that I can transfer. It looks like a big number. Now my Q max, I have an equation for this. So now I take my C min, so that's the fluid that's going to change temperature more, and I multiply it by the biggest temperature difference I can find in my heat exchanger. So I take C min and multiply that by H in minus, which is the hottest temperature, minus cold in, which is the coldest temperature. And if I do this, I see this number is bigger, right? And if I take these two numbers and divide them by each other, then I can find my effectiveness. My effectiveness for this heat exchanger is 0.69. So we have almost 70% of the maximum heat transfer we could transfer in this heat exchanger. So now that I've gone through and found the effectiveness, I can use the effectiveness in my equation for NTU to find NTU. So now before I didn't know the effectiveness. So I was here, I had my equation, I didn't know my effectiveness, but now I do know effectiveness. So I can put numbers into my calculator to find NTU. I find these equations are a little bit difficult to work with just because there's so much, brackets and pressing the natural log or taking the exponential term. So I do like to, I guess I always like to do this because I'm really good at screwing things up on my calculator, but I do like to sort of individually evaluate different parts of these things, right? So it's nice that my NTU value is positive. We should always get positive values of NTU. And in this case, I get NTU is equal to 2.25. So that's great. I know NTU. I feel like I should know NTU because it's called the effectiveness-NTU process. So now I'm going to try to use NTU to find the area, the size of my heat exchanger, right? And that's ultimately what the problem is asking me for. So now I go back and I use the definition for NTU. And the definition for NTU is that I take my effective heat transfer coefficient multiplied by my area and divide by C min. So this problem is nice. So I can rearrange this to try to find my area because that's what the problem is asking me for. This problem was nice because they told us the effective heat transfer coefficient. We didn't have to do any kind of internal flow to find that. I've already found C min and I already know NTU. So then I can go through and I can check to see that my area is 241.9 meters squared. You can see here that the remnants of the mistake I made on big C, so I still actually carried that through. So the units on big C should be watts per Kelvin, not watts per kilogram Kelvin. And if I do that, then I find the area, and that's what I've been asked to find. So here my message from Emily is that now you know, or now you have flaming knowledge. I guess flaming knowledge because we're talking about heat transfer, which is hot. So if anybody has any questions about the problem, we can go over them now. I hope seeing the example made it a little bit more clear, sort of how I approach these types of problems. And you can see, so there's 4 heat exchanger problems that are posted online, and I'll go through all 4 of them. So 1 of them today and 3 of them on Thursday. But we all follow the same process. I think that thinking about that 2x2 matrix at the beginning is really important. So I think that what we take away from this is when you have a heat exchanger problem, think about this 2x2 matrix. Because I think the hardest part of any problem that you might see on an exam is what do you do in the first 5 minutes, right? And if you think about this 2x2 matrix, then you'll say, oh, I'm just going to use this process. And I guess the way I'm trying to teach this is that once we know a process and we can pick one of these flow charts, whether it's for internal flow or external flow or now for heat exchangers, then we're kind of off to the races, and it's just about kind of systematically moving through the process. So I hope that that's helpful. All right. Does anybody have any questions? All right. I will let you go. I guess one more note. So I did grade and post grades for the second case study, so our final case study in this semester. And the other thing I did was I put up the grades for the team problems. You know, we used to be taking attendance on Thursday. And just because this semester has been kind of, a little bit weird, I just gave everybody 100% on that part of the class. So I think after that, we just have one more quiz, one more homework, and then the final exam. I think that those are the only graded events that are left. This is the last bit of new material. So next week I'll probably do a review lecture. And then I don't know. I'm a little bit open to discussing how we use the rest of the periods, or if we just kind of have them as open periods or periods where you work for yourself or more office hours. But that's all that I wanted to say. I don't know if anybody has any questions. It doesn't look like it. Okay. Thanks, everyone. Have a good day, and I will see you on Thursday.